In this video, we'll solve the initial value problem given by x prime of t equals 4x of t plus y of t, and y prime of t equals negative 2x of t plus y of t, with initial conditions x at 0 equals 1 and y at 0 equals 0. Now, we'll start this problem the same as we started the previous problem, and the first part is we're going to rewrite our system of differential equations in operator notation. So in order to do that, we're going to replace the x prime by d of x, and that is equal to 4x plus y, and then the second differential equation becomes d of y equals negative 2x plus y. Then in order to eliminate a variable, we're going to bring all the x's and y's to one side of each equation. And so for the first equation, we get d minus 4 of x minus y equals 0. In the second equation, we're going to take care of the x first to have it line up with this x here. So we're going to add 2x to both sides, and then we have plus d minus 1 of y, and that equals 0. Okay, second step is we're going to eliminate a variable, and I'm going to eliminate x here, and we can eliminate x by multiplying the top by negative 2 and the bottom by d minus 4. So if I multiply the top by negative 2, I get d minus 4 acting on x minus y equals 0. And for the second equation, I'm going to apply d minus 4, and I'm going to apply that to 2x plus d minus 1 acting on y, and that equals 0. And then I can add those two equations to get rid of my variable x. And what I'm left with for the y is negative 2 times negative y and then plus d minus 4 acting on d minus 1 acting on y, and that then on the right hand side, negative 2 times 0 gives you 0, and d minus 4 acting on 0 just gives you 0. So that keeps things relatively simple. And so now when we simplify this, we get 2y plus, and then when you multiply out these two differential operators, that's just foiling. So we get d squared and then minus 5d plus 4 acting on y, and that equals 0. And let's continue that over here. We have 2y plus y double prime minus 5y prime plus 4y equals 0. And then y double prime minus 5y prime plus 6y equals 0. So now our next step is that we want to solve this for y, and one of the nice things here is that this is a homogeneous equation. So note that this is homogeneous. And that means that there is no particular solution. So that definitely cuts down on the work for finding a solution. So let's find that solution in step 3. So we're going to solve for y. And in order to do so, we're going to take a look at the auxiliary equation. The auxiliary equation here is given by r squared minus 5r plus 6 equals 0. And that factors as r minus 2 times r minus 3 equals 0. And so the roots are r equals 2 and r equals 3. And therefore, a general solution for y is given by y of t equals c1 e to the power 2t plus c2 e to the power 3t. Now, what we have to do then is we have to take y that we found here and then plug it into one of the original equations. And again, either equation is fine, but there's definitely one that is less work than the other one. So we're going to plug in y and then solve for x. So since we want to solve for x, we want to pick the equation that is simplest for x. So the first equation has an x prime and an x, and the second equation only has an x. So that's the differential equation that we want to plug our solution into. So we're going to take the differential equation y prime equals negative 2x plus y, and we're going to plug in the solution, the general solution we found for y. So the derivative of this function is given by 2c1 e to the power 2t plus 3c2 e to the power 3t. And then that is equal to negative 2x plus, and then we have c1 e to the power 2t plus c2 e to the power 3t. So now let's solve that for x. We can bring this c1 e to the power 2t to the other side. And when we subtract that, we're left with c1 e to the power 2t on the left. And then we're bringing this c2 times e to the power 3t to this side. And my 3 looks a bit funky, so let me rewrite that. This is a 3, and so when we subtract that, we get plus 2c2 e to the power 3t, and that equals negative 2x. And now we divide both sides by negative 2, and we see that we get the equation x of t equals negative 1/2 c1 e to the power 2t minus c2 e to the power 3t. And together with what we found for y, we have this: y of t equals c1 e to the power 2t plus c2 e to the power 3t. Now, we still need to figure out what c1 and c2 are, because we're given some initial conditions here. So our initial conditions are given by x at 0 equals 1 and y at 0 equals 0. So what that implies is that when you plug in 0 for x, you get 1. So on the right hand side, we get negative 1/2 c1 e to the power 2 times 0 minus c2 e to the power 3 times 0. And for the second part, we get that 0 equals, plugging in 0 here gives us c1 e to the power 2 times 0 plus c2 e to the power 3 times 0. And that simplifies to the following: 1 equals negative 1/2 c1 minus c2, and we have the 0 equals c1 plus c2. Now we can add these two equations and c2 will cancel out, and then what we get is that if we add this up, we get 1 and then plus 1/2 c1, or 1 equals 1/2 c1, and then the c2's cancel out, so we're left with c1 equals 2. And then when we plug that into one of these two equations, let's do the second one, we then get 0 equals 2 plus c2, and that means that c2 equals negative 2. Now, if we use those two coefficients, c1 equals 2, c2 equals negative 2, and plug them in here, then our solution to the system of linear differential equations becomes xt equals negative 1/2 c1, so that is minus e to the power 2t minus c2, so that becomes plus 2e to the power 3t. And for y of t, we get c1, which is 2, so we get 2e to the power 2t, and then plus c2, that gives us negative 2e to the power 3t. and that gives us the final answer to our problem.